Today's the day of shooting more rays through the scene. We're going to deal with reflection and refraction in computer graphics in the summer term of 2025 at Bocholt campus of Westphalian University of Applied Sciences. G'day, another topic for ray tracing, but before we can go there, we need to finish last time. I skipped the normal transformation, and today for creating reflection and refraction rays, we need the normals, so we better have them correct before. Okay? So let me pick up the slides. Where are they? Here they are. Is that? And you don't see anything behind me other than the preview of the next slide. Let me fix that for a moment. That should be it, and we have the slides up there. All right, I see the preview, you see the slides. The slides are on the big screen, and I think we're ready to go. Okay, 3 triangles. In fact, only one triangle that gets tilted a little. And since a triangle is made up of 3 points, where 3 points define a plane, the triangle lives in a plane, right? And the plane's orientation can be represented by the normal, by a normal vector that I can denote with a vector arrow and an N, and it has one property regarding, or property concerning the plane or the triangle. What is it? What property does a normal have? The normal sits orthogonally on the surface. On the plane, on the triangle, it's all the same because the triangle lives in the plane or sits exactly in the plane. So the triangle's orientation can be either represented by the plane itself or the normal perpendicular to that plane, right? And wherever I orient the plane, or however I orient the plane in 3D space, the normal comes with the orientation or changes accordingly to still be perpendicular to the plane. Okay? Good. Let's take 3 vertices of the triangle. How can I compute the normal? Because if I just have the triangle in my scene, in the end, I need to do some illumination on the triangle, or for each point on the triangle, or in ray tracing terms, for each pixel that shows the triangle, I need to compute the illumination. So I need to know the normal of the triangle. How do I compute that? Just throw the cube to the back, please. So you need to compute a cross product, and the cross product of 2 vectors in the plane. And since you only have information about V0, V1, and V2, the 3 vertices of the triangle, you need to create those vectors in the plane from the differences between 2 vertices. And these are 2 differences where this works. That is the difference V1 minus V0, which is the vector starting at V0, pointing towards V1, and V2 minus V0, which is the vector again starting at V0, pointing at V2. And since this is a triangle, both of these vectors enclose an angle that is smaller than 180 degrees. Otherwise, it wouldn't be a triangle. So I take this vector starting at v0, pointing at v1, taking the second vector starting at v0, pointing at v2. And then you need to use the right-hand rule again. If you start at the first vector and turn all the way to the second vector, you get from the cross product another vector that points orthogonally out of the plane. Or you take your three fingers of your right hand, you take the first vector and the second vector, and let me just try it. So this is the first, this is the second, and then the other one points in the direction of the normal. And since this is some sort of sketch of the perspective that is in place here, it doesn't match with my hand. But that's the way to compute the normal. The cross product of two vectors in the plane, and then you get one vector that is perpendicular to both input vectors. Why do I divide by the length of the resulting vector? What does this division do? What do you know about n afterwards? Just catch the cube. So after this division, after dividing the cross product by its length, you get a vector of length 1 or a normalized vector. So this is the vector that carries only the perpendicular direction, but no length other than 1. It's just a vector used for the direction that is perpendicular to the plane that we're interested in, but it does not scale any other vector if we use it. That is why we need to use length 1 or unit length for all the other computations that we're going to do later, especially in illumination. Because there you compute the dot product of the light vector and the normal vector, or if you're doing Phong, you compute a reflection vector using that dot product. And if the normal vector has a length other than 1, you scale the dot product, because then it's not just only the cosine, then it's the cosine times the length. And since the length is 1, you can even leave this factor out. Well, that is why you need to make sure that the factor is 1 and that the length is 1. Okay? Cross product gives you the normal. All right. Coming back to last week, we can do transformations. So we can move V0, V1, V2 around in space. We can scale the triangle. We can rotate the triangle. We can even shear the triangle, an operation that I did not show you last time, but that is basically taking the object, and let's say this is the coordinate system's origin, taking the object and, no, let me do it that way, and just moving, doesn't work, just moving it that way. So just moving the upper end of the rectangle, so tilting it that way. Let me draw it, as you know what shear is. That is another operation that we can do, but I did not show you how it works because, in the beginning you rarely use shear. So what does it do? It works that way. Take a rectangle, and let's say that is the coordinate system. So this is x, this is y, you have the rectangle, and you shear it in this direction, and the result will be, again, the coordinate system with the bottom side of the rectangle. You basically move the topmost side rightwards. So you end up with this figure. That is shearing in the x direction. It also works in the y direction and in the z direction. And then you can basically somehow deform or skew any of your objects. All right. Anything of the shearing, rotation, translation, and scaling are those operations that you can apply to all of your objects in the scene. So basically to all of the triangles in your scene, if you model everything with triangles. And since you only have the information of the vertices of the triangles plus the connection information, so which vertex is connected to which other vertex, the only thing that you can transform are the vertices. And then you can think of how to transform the normals. Why not also rotate, scale, translate, and shear them? There is another vector that you can compute for each triangle. And if you can transform those, it's just basically, again, a matrix times another vector in order to get the transformed normal, so that you don't need to recompute the normal after transforming the triangle. All right? So, looking from the side, you take your triangle with the normal, and, for example, scale the triangle and the normal, and try to scale the normal with the same matrix. And this should be a scaling by a factor of 2 in the x direction. And y and z were scaled by a factor of 1. What do you think about the normal after the transformation? Is this still a normal for the transformed triangle? Well, it got longer, so it's not normalized anymore, but it isn't perpendicular anymore. Well, the good thing is this does not happen for rotation. This does not happen for translation, because you can't translate a normal, or you don't change a normal when translating it, because it's a vector sitting everywhere in space, basically. It doesn't happen for uniform scaling. It only happens for non-uniform scaling, where you say one direction scales differently than the others. And it happens for shearing. So if you want to allow non-uniform scaling and shearing, you need to take care of this. You need to make sure that you have computed the normal correctly if you apply transformation. And so it seems there needs to be a different matrix at work, a different transformation matrix at work, this one n, that transforms the normals, in order to keep them perpendicular to the surfaces. Right? So basically, vertices transform the way we did last week. We need to find an alternative way to transform normals. Any idea how to do that? Let me just check for the moment if I can somehow come to the sheet where I took notes. There it is. So, how to compute n, uppercase n. Okay, we'll do it on the blackboard. And I guess we can do it on this one. What do you know about the normal prior to transformation? So we have a surface. Let's say bound by v0 and v1, which has a normal n being defined. And this normal n is perpendicular to the surface. So it is perpendicular to a vector t, tangent to the surface. And in this case, this is at least parallel to the vector going from v0 to v1. Okay? What do you know about this dot product? Move out of the way. What do you know about this dot product if both vectors are perpendicular to each other? What is the definition of the dot product anyway? Okay, just try. So it should be 0 when there is a right angle, because the definition is the length of n times the length of t times the cosine, no, it's just cos, of the angle in between them. This is theta. This length should be 1. It doesn't really matter. But if this is just a tangent vector, then this should also be 1. But in fact, it does not matter either, because the cosine of 90 degrees is 0. Okay, so this is 0. Okay. Now let us transform this to say v0 dash to v1 dash, which gives a tangent vector t dash that is also transformed. And we need the new normal n dash perpendicular to the tangent vector. What do we know about n dash transposed times t dash? And this is just again a fancy way for writing the dot product. What do we know about the dot product after the transformation? Or better, what do we require the dot product to be after the transformation? The result needs to be 0 again, because we want to preserve this right angle. Okay? Good. Then let's start with this product. How can I rewrite this term and change nothing? Which factor can I add that does not change anything in a multiplication? If I multiply anything by 1, it does not change, right? Can you think of a matrix, or the matrix equivalent of 1 changing nothing? Because we're having matrices here. Yes, they look like vectors, but I use the transpose operation, so I can say this is a row vector or one row matrix, this is one column matrix, product works. But we need a matrix that does not change anything in a product. We need the identity matrix in this case. But where do I put it? If I put it here, what is the result? Matrix times the dot product. Does it give me 0? It gives me the it gives me 0 because there's the identity matrix, but it is a matrix with all zeros. It's not a single 0. The same applies if I put it here. So I can say, okay, this is a row vector times the identity matrix times the column matrix. And then I transform this column vector with the identity matrix basically to itself. A column vector, matrix times a column vector is a column vector, but it has not changed because this is just a factor 1 on speed, if you will. It's just a matrix of 1s on the diagonal. And then I do the dot product, which still is 0, right? So just to make sure, I, in this case, is the matrix 1, 1, 1, 1. And everything else is 0. One's on the diagonal, everything else is 0. How can you generate the identity matrix? Which multiplication generates a 1? And if you do it in matrix terms, which matrix multiplication generates the identity matrix? Especially if you take one matrix that you should already know that is involved here. But let's first say which number multiplied by which other number yields 1. Let's take a 17 for starters. By which number do you need to multiply 17 in order to get a 1? Yes, 1/17 or 1/17. Let's take 125. What is the factor you need to multiply to 125 in order to get a 1? It's 1/125. And what would you call this 1/125 if you were to name the operation? How is it related to the 125? If you think a bit in the future, we will have a matrix that we need to multiply by another matrix, and we need to name this other matrix. Yeah, it's the inverse. A factor of 1/125 is the inverse of the factor of 125. You could call it that way, because in matrix terms, if you multiply any matrix, M, by its inverse, it's even written the same way. 125 to the power of -1 is 1/125. So if you multiply any matrix by its inverse, what do you get? The same as you would get by multiplying any number with its inverse. You get a 1, right? But this needs to be a matrix of all 1s on the diagonal, so this is our identity matrix, right? Okay, so rewrite this once again. It did not change, right? What is this matrix? Do we know that already? Do we know that matrix? Since we're looking for the transformation matrix that is applicable to normals, why not take M as the matrix that takes you from here to there, so as the matrix that transforms T into M, or that transforms any vertex into the transformed vertex. Okay? Then, what is that? If we say M is the transformation matrix for which we're looking for a normal transformation matrix. That is T dash, right? Okay. And if this is T dash, this is that zero, what do we know about this? Well, I need to get the -1 in here. Well, this is a three-part equation, if you will. Part 1, part 2, part 3. We already know 2 of them. There is no way that this is not the orange box. Right? So, the transpose of the transformed normal, a row vector of the transformed normal, is the transpose of the original normal times multiplied by the inverse of the transformation matrix. Careful, this is row vector times matrix. This is matrix times column vector. So this works. And still yields a row vector. Row vector times matrix yields a row vector. How do we get this to be n dash? Well, transpose both sides. You can rearrange this equation with a transpose operation. If you transpose both sides, they are still equivalent. And then how do you transpose the product of 2 matrices? And it doesn't matter that this is a row vector. This is still a product of 2 matrices. So all the rules apply. How do you transpose the product of 2 matrices? You transpose both of them and you flip the order. So the transpose operation applies to this one and to this one, and you need to flip the order in the product. So this is M inverse transposed times N transposed again. And what is the transposed version of a transposed vector or matrix? That is just n, because if you take the column vector, transpose it to a row vector, and transpose it back to a column vector, you end up with what you started in the beginning. Okay? So those two transpose operations cancel each other out, if you like, or cancel each other. And then we're done. Because that is the matrix N that we were looking for. Okay? So you take the inverse of the transformation matrix that you use for the vertices, transpose it, and use it for the normals. Okay? And since we're talking about affine transformations, this is the same as the inverse of the transpose, but that does not help us that much. Why does this notation help us more than this one? How do you compute M in the first place? That was, for example, a rotation matrix, a translation matrix, a scaling, another translation, another rotation, and another scaling. Okay? That is the first operation. Careful, you need to read it from right to left. You first translate the object, because in the final multiplication, this operation is closest to the vertex. So any vertex gets first translated, then rotated, then translated again, then scaled, then translated again, and finally rotated. Okay? We can compute this matrix by just multiplying them together, according to the rules that we know. Okay? And then we could transpose it. That's easy, just flip rows and columns. But how to invert a 4x4 matrix? Well, first of all, let's hope that this is invertible, because we just have a matrix. We need to first check that it is invertible. Well, not quite, because we need to compute the determinant. And then we need to find, 16 adjunct matrices in order to come up with a 4x4 inverse matrix. A bit complicated, right? Well, if we do it the other way around, first invert it and then transpose it, then the end is easy, because we just need to flip rows and columns, or swap rows and columns. But we still need to invert the matrix in the first place, so let's hope this is invertible. And again, we need to compute the determinant and all the adjunct matrices. Or is there any other way? Can you think of another way of computing the inverse matrix for this transformation? Any idea? How can we do it? Okay, let's say this is it visible in the video? Yeah. The lower left corner of the blackboard is the origin. I first translate a point halfway along the x-axis and halfway along the y-axis. I end up here, right? And then I scale it by a factor of 2 in order to end up here. First translate, then scale. How do I invert this operation? First, scale it back, and then translate it back. Okay? I also could have asked, how do you compute the inverse of a matrix product? It's the same as how you compute the transpose. The inverse operation is applied to each individual factor, and the order is reversed. So this is T1 inverse times R2 inverse times T3 inverse times S4 inverse times T5 inverse times, what was it, rotation 6 inverse. Well, glad that we did that, going down from 1 matrix to be inverted to now 6 matrices to be inverted. That was a neat trick, right? Okay. If I translate myself, taking my coordinate system, 1 step to the left, how can I translate myself back? I could take 1 step to the right in order to get me back to where I started. And 1 step to the right is the same as minus 1 step to the left. So translation is easy. It's just taking the same translation times minus 1. Careful, don't put the minus 1s on the diagonal, just put the minus 1s on the tx, ty, tz in the 4th column. Okay. If I scaled myself up by the factor of 3, how would I get me back by just scaling me? Yes. The inverse of a scaling with a factor of 3 is scaling by 1/3. All right? And if I now rotate myself 45 degrees in positive direction about my up axis, how do I get myself back? Again, minus 45 degrees rotation around my up axis. Okay? So computing the individual inverses is pretty trivial. Just taking note of what you did on the forward way and apply it in the opposite direction on the backward way. And since you can apply all the transformations one after another to the object, you don't need just to accumulate m, you should also accumulate m minus 1 or m inverse in order to have the matrix ready that is required for transforming the normals. All right? And if you look into the documentation of 3D engines or modeling toolkits, you will certainly find that the objects carry a matrix and an inverse matrix. Because if you apply those operations one after the other, it's way cheaper to compute the inverse as you go while computing a forward matrix. Okay? How did we end there? Well, just by introducing a factor of 1, finding a fancy way of writing it, and then just comparing this line with what we have written initially. Okay? So nothing big to it, really. Okay? And that is how you transform normals if you want to allow for non-uniform scaling and shearing. Okay? And it's no problem to compute this n. Well, the transpose operation is pretty easy. And the computation of the inverse is also straightforward. You just need to add another 16 float values to each object. Okay. So, any questions for this one? Yes. So you basically suggest to take this product, rearrange it, or with the identity matrix, try to figure out what this matrix should be. So this is just it should be solving a system of linear equations. Well, that is much more complicated than doing it that way. Because the moment you apply the transformation, you can immediately apply its inverse and don't need to take this matrix and compute the inverse by rearranging the matrix or trying to figure out how to solve this. It should be just solving a system of linear equations, but just that is the problem. Is it? Well, by the way, it wouldn't work with a determinant and adjunct matrices, would it? Should. Maybe. Yeah, there are ways to invert a matrix, but this involves at least the determinant in order to check if it's invertible, and you need to have the determinant ready in order to compute the inverse. But computing the determinant should be more expensive than just doing this as you go. All right. And even more so, depending on when you compute the normals, or the transformed normals, it could be that you need to compute the inverse matrix for each ray and then for each object or each triangle. And that would be much more expensive if you just said, well, take note of the inverse matrix as you take note of the regular matrix. And by the way, even in rasterization, what we will do, I think, maybe next time, you need both matrices anyway, depending on what you are computing. All right. So that is transforming surface normals. We can now do more math for, let me just open it, set it up properly. Next page. For coming to the topic, that is the problem. No, I don't Want to spill the beans? Next slide. Doesn't work. The projector ended. Ah, it's still blank. Here we go. That is the topic of today. Reflection and refraction. Fortunately, one half of the problem is already solved, and you might recognize where this is coming from, but we should have a look at this guy again. Is there reflection in there? Perfect specular reflection? Because that was just illumination, and we ended up in doing the green shading with some specular highlights. If you look at this equation with a certain numbers of steps in the distance, or from a distant point of view, this is again our sum over all incoming light. It might be an infinitely long sum, but it's the sum of all incoming light. And, well, again, this is wrong. That is the incoming light. So this sums up all the incident light. Don't take the excitant, it's the incident light. And for each of those incident directions, you have a factor, depending on the surface material, that says how much of the light is scattered into your eye. This could also be how much light is perfectly mirror reflected into your eye. There is one problem with this cosine term here. This might turn infinite for mirror reflections, or on the direction of mirror reflections, but it doesn't matter. If you read it that way, sum every contribution, every light contribution, take the incident light from that direction multiplied by the factor that is required in order to cancel the cosine term for mirror reflection, and this still works. And the same argument would apply for transmission, but then it's not a reflectance distribution function anymore, then it's a scattering distribution function. But it doesn't matter, it's still a factor that tells you how much light comes through the object. How much light that is incident to the backside of your object goes through it into the direction of x3, aka u. Right? So it's in here. Now we need to figure out how to compute the direction of the reflection ray in order to trace it. Right? Because we ended in a situation where we shoot the rays from our eyes into the scene and they hit objects. If they are reflective, we need to trace another ray that collects the reflection from the object. All right? And we need to know the direction of this reflection ray. Does that ring a bell somehow? Which one? Yes, we talked about that, and we started with this graphics for Phong illumination. There you also need the reflection vector in order to tell if you see a specular highlight or not. So these shiny points on polished surfaces. But that is just or an approximation of the perfect mirror reflections of light sources. Now we want to do reflection of other objects. But it's the same rule. You have in this sketch the light vector, but the important part is you have an incident angle and an excitant angle, and they are both equal for the reflection vector. So you can still use this graphics. I just need to check this one. Need this one. In order to come up with this version of it, where you say, okay, S, the side vector, is minus L plus U, and this was for the light vector, so you have the point and look to the light. Unfortunately, if you take the viewing ray, you look towards that point, so minus L is the direction of the incident ray. Okay? You take this U, because you need to somehow split it, and after having split it, you end up with this final form, minus L, aka D, plus 2 times N times minus D times N. And maybe this version was the one that resembles the final step better. Okay? So you already can compute reflection rays, because you are able to determine a reflection vector in illumination, and with the same set of tools you can compute the direction of a reflection ray. It's just the same that I showed you for Phong illumination. So you're already done with reflection. You can already implement it. If you can do Phong illumination, or if you can implement the Phong reflection model, you already have the equations to use for reflection rays. Just be careful. This is an L, the vector from the intersection towards the light point, and you have the direction from the eye to the intersection. But it works the same. Okay. Just waiting until the note-taking has finished, and then we can switch over to refraction. The other half of the lecture that takes longer than the first half. But that is because we need to do the math today, and we already had the math in place there. And I don't think, if I keep on writing that big, that I can keep it on one board. I just clean the other, then you can finish taking notes of this equation, or maybe just take a short break. Let me just open the microphone again so that everyone can hear it. This is an object. We have one surface here, and there the other surface, and a ray, a light ray, hitting the object. It will somehow pass through it, but how will it do it? Mm-hmm. Yeah. Yes, correct. So if this is glass, then there will certainly be some amount of light being reflected off the surface, but this is reflection and you can deal separately with it. You already have the equations. There's just a reflection vector, create a reflection ray and trace it. Parts of it will, parts of the light will go through the object, and that is correct. They will change direction. It will be bent, enter the material, and then it will be bent again when exiting the material, right? And if you add the normal, you can see that there are two angles where theta 1, the angle on the outside, is larger than the angle on the inside, theta 2, and this is due to the fact that the medium on the outside is not as dense as the medium on the inside. So if you as a ray of light enter an optically denser material, you will get bent towards the normal, right? And this is what Snell's law tells you. We're just saying that eta 1, this guy here, the refractive index of medium 1 times the sine of the incident angle, theta 1, is equal to the refractive index of the second medium times the sine of the excitant angle on the other side. Right? And this leads to, in the optical denser medium, light is refracted towards the normal. Okay? All right. Sorry for the break. Where have we been there? Right. So, thinner medium, denser medium, thinner medium. Light is entering from the thinner medium into the denser medium, and it gets bent towards the normal while entering. The denser medium, and on the other hand, when entering the thinner medium, again, it gets bent away from the normal. Right? And that is the case here. With the extra, if you like, if you enter from a thinner medium into a denser medium, and into the first medium again, where it doesn't matter if eta 2 is really for a denser medium, if you enter from one medium into another, back into the first medium, for two parallel surfaces, that is important, you end up with a final excitant angle equal to the original incident angle. All right? If you want to do this realistically, you need to respect the colors that travel through the medium. And since you are respecting the colors, you will see that blue light gets refracted more than red light. So the shorter the wavelength, the greater the degree of refraction. Right. Does this create a rainbow? Is this dispersion effect the reason for rainbows to appear? Well, certainly yes, but is this the sketch you want to look at for rainbows to appear? Yeah, for rainbows to appear in the sky, you need water drops. And if you want to look at a famous CD cover, or record cover, it looks differently. Because that does not create a rainbow. You will see white light on the other side of the glass. Why? White light is entering the glass. And if you believe this sketch or this drawing, you would see the blue light exiting higher than the red light. But why does white light come out of the glass? Because here is another ray of white light entering the glass, being dispersed a little, and then the green part of the second ray mixes with this blue light. And if you take a third ray entering here, being split into the individual colors, the red light of this third ray will mix with the blue part of the first ray. So white light exiting. Well, getting back to the record cover, you have white light hitting a prism, being split into the individual components, and then being split even more when exiting the prism. And that is how to generate a rainbow with a prism. You don't have the parallel surfaces, which you have here. And since you have parallel surfaces here, the incident angle is equal to the excitant angle, and the split up light rays mix across the rays, or the split colors mix across the rays, which doesn't happen for a prism. Okay? Good. Just to make sure this does not produce a rainbow, this is just an infinitely small ray of white light that will be split into an infinitely small rainbow. But since there are multiple infinitely small rays of white light, all the rainbows mix again to create white light. But here you'll see a rainbow. All right. We still need the direction of the transmission ray. And you need to compute it in order to create transmission rays. Let me just make my notes a bit larger and switch to the blackboard again. Shall I do it that way? No, the other way. Let's start with this one. We have the interface. We have an incident ray, excitant ray. We have one theta here, one eta here. And let's say this is the eta on the incident side, and this is the eta on the transmitted or transmitting side. Then this is, where do I put it? Here, direction of the transmitted ray, and this is the direction of the incoming or incident ray. Okay? We can sketch the normal. That is this guy. Okay? How to compute dt. Well, let's do the same thing that we did for the reflection, or a similar thing, but to the other vector. Let's say we have one vector here and another vector here. So there is one part of dt that is orthogonal to the surface, part of dt that is orthogonal to the surface, and here is one part of dt that is parallel to the surface. And both create dt. Right? We can decompose dt into two individual vectors. One orthogonal to the surface and one parallel to the surface. And the same, and we can do the same for di. We have a component of di that is orthogonal to the surface and a component of di that is parallel to the surface. Okay? So we have di equals di orthogonal plus di parallel. Okay? That is theta I, that is theta t. The angle on the incoming side and the angle on the transmission side. Okay? What did Snell's law tell us? Because that is the thing that is in effect here. Well, that was eta I, what is it? Is it the refractive index? That is the word. The refractive index of the medium on the incoming side times the sine of theta I, the angle on the incoming side, is the same as eta on the transmission side times sine of the angle on the transmission side. Okay? Just rearrange it in order to come up with the sine on the transmission side. That is eta I over eta t times sine theta in. And what do we know about those two guys if we say, where do I put it? Yeah, let's put it here. The length of di equals the length of dt, and both are 1. How does this help us? Because this is just a ray direction, and it's always helpful to normalize directions because it simplifies equations a lot if we just need to use 1 instead of any other factor. How does this help us? Just once again, this is a right angle. This is a right angle, so those are right triangles. This is di. This is dt. We know the length of it. Both are 1. It's terribly drawn, by the way. This is the length 1, and this is also the length 1. But it doesn't matter for the sketch. Can you see the sine of the thetas in the drawing? di2, that's just the parallel sign, but it's the two pipe characters to denote parallel and perpendicular in this case. So yes, it's the length of di, the parallel component of di, that is the sine of theta I, if this side is 1, and if this side is 1, then the sine of theta t is the length of this side. Right? So this leaves us with sine of theta in is the length of di, the parallel component, and the sine of theta t is the length of the parallel component of dt. It's just the length of the side of the triangle that is opposite to the angle if this side is 1 and this side is 1. Okay? So this means what is written here is just the same as the length of the parallel component of the transmission ray. It's the same as eta I over eta t times the length of the parallel component of the incident ray. Okay? Just by using trigonometry. What is the direction of the parallel component of di and the direction of the parallel component of dt? Just the direction. Where do the arrows point? Where do both arrows point? Downwards. All right, they point in the same direction. And This vector is parallel to the surface. This vector is also parallel to the surface, so they are both parallel. Right? So, di parallel and dt parallel are parallel vectors pointing in the same direction. And this means that I can multiply both sides with the direction of unit length pointing in the same direction as di parallel and dt parallel. Now, what does it mean? If I multiply this by its direction and this by its direction, which is the same, it's unit length, it's pointing in the same direction, and both are parallel. That is the length of a vector multiplied by its direction yields the vector itself. This is dt parallel is equal to this fraction times di parallel. It's just multiplying it by the vector, by the direction, by the same direction vector. The direction has unit length, so it doesn't change anything on the scaling. It just adds back the direction into the equation, and this is possible since I was to write the d. Since both are pointing in the same direction and both are parallel, this is just the same. Okay? How does this help me? How can I say anything about dt if I start here? Is there anything missing that I need to add in order to come from dt parallel to dt? What is missing? dt equals dt parallel plus, come on, yes, dt perpendicular. No, not dt perpendicular. Yeah, dt perpendicular, dt perpendicular. That is dt parallel plus dt perpendicular yields dt, right? What is di parallel? What is di parallel? What about di minus di perpendicular? This vector minus this one yields that vector, right? Why is it good to have perpendicular vectors in place? So this one and this one. How do we know how to compute those? me check one thing. Yes. Can we compute this one? So we can compute the perpendicular part by using a cosine, but let's take the cosine on this side because we need to find the cosine. The cosines are much better suited for vectors in terms of computer graphics because they are maybe related to the dot product. And let's not do the cosine here because we don't know the angle, but let's take the dot product instead. Right? So the perpendicular part is just projecting this vector onto the normal, yielding the length, multiplying it by the normal, yielding its original direction. Right? So this is eta I over eta t times di, which we know, minus di transpose times n yields the, is that? Yeah, that yields the length. Di transpose multiplied with a normal yields the length, that is the dot product. And if I multiply it with a normal, I get the vector along the normal. Right? Incident vector. So vector in this direction, forming the dot product with the normal, yields a negative number, the length, negative, times the normal, adds this direction back into the vector, with a minus flipping it into this direction. Here was a minus, there was a minus, so it works. Okay, and let's just put this into parentheses, that we have the product again. Okay. And then again, plus cosine of theta t, as you said, which yields the length times the normal in order to give it a direction. But now careful, the normal is pointing that way. dt perpendicular is pointing the other way, so flipping the sign, minus. All right? We know the etas, we know di, we still know di, we know the normal, we still know the normal, we need to find cosine theta of t. Is that the same as I have written down? With an overall minus, that is, and that is a minus. Yes, that should be correct. How do we find the cosine theta t? What do you know about this sum? Sine theta, take sine theta and square it. It's written as sine squared theta, plus take the cosine of theta and square it. What is the result? That is 1. That is 1. So, the cosine theta t squared is 1 minus sine squared theta t, right? Missing a square in my notes. Right, and what do you know about the sine of theta t? Do you know anything about the sine of theta t? It's up there. Sine of theta t is eta I over eta t sine of theta I. Right? That is Snell's law again. So, entering it back here, so this is just a side note, so the cosine squared of theta t is 1 minus eta I squared eta t squared sine square of theta I. Right? So the cosine theta t is the square root of 1 of this guy. Right? Okay, so starting from trying to find dt, a whole vector in the direction of the transmission, we ended up with the only unknown, the cosine of theta t. This now takes us to the sine of theta I. Well, still a trigonometric function, but the sine of an angle created by a vector that we know. Right? What do we know about the square of sine theta I? It's written just immediately to the left. Yes, 1 minus cosine squared of theta I. What do we know about the cosine of theta I? Remember, the length of di is 1. And whenever you need to take the cosine, it's much better to take the related dot product. And the related dot product is the dot product of di and n, which yields a cosine, and you need to square it. Let's just briefly check sines. The cosine of theta I is positive. The dot product of di and the normal is negative because both point into opposite directions. Do we need to account for that? Yes, we are squaring the dot product, so the minus sign does not matter. All right? We're done. That is the direction of the transmission ray. In order to get the direction of the transmission ray, you need to know cosine of theta t. Cosine of theta t is that square root. If I'm not mistaken, we need the squares here, right? Because I'm squaring the sine, and the sine is related to, the one sine is related to which one? Yes, this sine is related to this sine, so we need to square both. So that should be the correct term on this side. The cosine of theta squared is this one, so the cosine of theta t is the square root of this one. The square root contains the sine squared of theta I, and the sine squared of theta I is, according to the Pythagorean theorem, this one. And that is all you need, in air quotes, all you need in order to come up with the transmission direction. Who of you did sines and cosines in school? Honestly. All the other ones didn't do it in school? Even if it's long ago, you all did that in school, right? Did you do the dot product of two vectors in school? All right, it depends on which course you took, I guess, maybe. Well, let's say at least half of you had all the math that is required here in order to come up with more photorealistic ray-traced images already in school prior to the A-levels. Right? So nothing really fancy here. Well, it's a bit heavy to compute, yes, but all the mechanics and all the tools you need are already present. But unfortunately, long ago, and no one told you that you can do refraction rays when you learned sines and cosines in school. Right. Good. So, let me check my notes. If that is all, yes, that is basically it. Coming back, one slide. Back here. Well, what is not on the summary is the transformation of normal vectors, which we did as a leftover from last week. We talked about the reflection vector once again. We already had this in the Phong reflection model, so you should be somehow familiar with it. You should have learned about Snell's law in school, or maybe here in physics, hopefully. At least it's not that difficult to write down. And from that, only with the math tools most of you learned in school, we derived the direction of the refraction ray that you can use in ray tracing. Okay. If you do this, if you trace a ray from your eye into the scene, hit an object that is maybe a glass ball, as in with its original image, you will have reflection going on, so you reflect and therefore trace another ray off the surface of the sphere into the scene, and you trace another ray through the sphere, the transmission ray or refraction ray. Is there anything that could go wrong if you do it with the data types available to you if you're programming a computer? There's no problem at all if you were to do it on paper. It even works in reality if you're looking at a glass sphere. There is reflection in place and there is refraction in place, and it works perfectly. But what does go wrong if you were to implement this using float or doubles? There will be some rounding issues, and you will see them in the final picture. I don't know if there is a name for the effect for reflection and refraction, but there is for shadow. It's called shadow acne. And since we're doing reflection and refraction, from the eye, tracing the primary ray into the scene, you will hit the surface of the object. But depending on where you hit the sphere and which numbers you get out of those equations, one pixel will show you the intersection rounded out of the sphere, and the other will show you the intersection rounded into the sphere, just slightly. But if you then shoot a reflection ray from outside the sphere into the scene, there's no problem at all. If you shoot the reflection ray from inside the sphere into the scene, you might end up immediately hitting the sphere again. So basically not showing you the scene, but showing you the inside of the sphere. And the same applies, just vice versa, to the transmission ray. If you try to trace a transmission ray from the outside of the sphere, not from the surface, but slightly from the outside of the sphere, you're going to hit the sphere. Maybe. You might end up with rounding differences again that take you on the inside so you don't see it. So there may be some flakiness in the reflection and the refraction, which you also see for shadows, because the same applies. The primary ray might intersect the sphere or any object, and rounding to a float or a double might just get you slightly into the object. And if you then trace a shadow ray, you might not see the light source because you're immediately hitting the object that should receive the shadow again. But it's fairly simple to come up with a solution to that. Just account for the rounding issues. Okay? Good. Anything else to add or questions to ask at this point? All right. Then that was normal transformation, reflection, and refraction in terms of ray tracing in computer graphics in the summer term of 2025 at Bocholt campus of Westphalian University of Applied Sciences. Thanks for watching. See you next time.